This is lecture number 4 of Civ 360. To quickly review, we have now considered two states of stress. So we go from displacement to strain to stress. But now what we realize is it's not just sigma. Sigma is actually our symbol for normal stress, but we also have a shear stress here. So using the sigma is really more symbolic or a mnemonic. In other words, it's a memory device to help us remember it's just stress. But now we have two measures, and incidentally, then we go to force. So we have these measures, and once again, they are point-wise measures of force per area. So they are a force per length squared, and there are a total of 6 components of those that are going to be independent. So at this point, we're pretty much truncating our discussion on stress for now. We're going to come back to it, obviously. And now what we like to do is focus on our next particular symbol, and that's going to be the subject of strain. In fact, let's put a box around this. So this is our big topic. And we're going to start with the simplest possible construction that we could possibly introduce. Sorry for two uses of the word possibly there. And that's going to be if we take our friend, the axially loaded bar. So a 2x4, a piece of rebar, a wooden dowel, and we load it. We load it with some sort of force P. And let's say that the bar then is originally of a length L. Like so. Now, as we've been saying, as a elastic solid, or as a solid that's deformable is loaded, it deforms. So let's say we go ahead and pull on this thing, and it moves. And it's going to move the amount that we're going to call delta. And we'll call that the axial displacement. Now you might be wondering, wait, why don't you call it U? We've been using U as our symbol for displacement. Delta is actually the specific sort of symbol that we use for an axially loaded system. So delta is just going to be kind of an ad hoc designation for the axial stretch that we have inside of a bar. So now we are in a position to define one quantity, and we're going to define it like this. So we define epsilon. So that's the Greek letter epsilon. The Greek letter epsilon, and we're going to put an AVG, and that's for average. So that is called the average normal strain. So again, this is our first definition, our first introduction to this concept. And it basically amounts to the change in the length divided by the original length. In other words, the average normal strain is going to be the delta divided by L. And we're going to put a dash box around that, not because it's not a final result, but we've got a little bit more work to do before we can kind of figure out what that's going to be. So the normal strain, average normal strain, is equal to the change in length divided by the original length. But unfortunately, that's not really going to be all that functional for us. And here's why. Let's say that I didn't tell you that the left half of the bar is made of aluminum, and the right-hand half of the bar is made of silly putty. Hopefully you guys still know what that is. If not, think of chewing gum. So what if we had something like this? Well, then almost all of the deformation would go into the silly putty section. The aluminum barely moves at all. So we'll say lots of stretch. I'll say lots of delta. And this does not move much. Not much delta. And so we realize that it's not good enough to get an average. It's not going to be comprehensive enough for us to use in all circumstances. And what we decide to do instead is to get some sort of point-wise measure. So get a measure of this change in length per unit length point-wise. So get a message pointwise. There's that word again. Now for stress, the way that we did that was we surrounded a cut area with a small area. That's not quite what we're going to do right now. What we're going to do is we're going to go inside of our line. And I'm going to put a line element like this. I'm going to give it a bigger distance than we might normally do. And we're going to call that length delta x. So x is our axial coordinate as we've been considering before. By the way, this is the same axially loaded bar. So we've got the axial loaded bar with P at the right-hand end, aluminum and silly putty. We're going to identify a line element length of delta x. Now let me blow this delta x up. So blow up our line element length delta x. So I'm going to sketch that down here. Sorry about that. There is our line element length of delta x. And now I am going to go back to u. So I'm going to say at the left-hand end, so if this is my original coordinate, and I can put x right at this location, then at x we have u at the location x. Maybe I should put a distance in here. That would have been a better way of doing it. So this is equal to the axial displacement, or the left and right movement. In this case, I'm assuming it's going to be going to the right. The axial displacement at point x. So that is u of x. So the axial displacement at some point x. Then I have the right-hand end of that little line element, and that's going to be u at x plus delta x. So in other words, I'm going a little bit of distance and I'm getting a different sort of axial displacement. So I have two axial displacements, u at x plus delta x, u at x. Well, now we can see that the delta between that is just going to be the difference between those two. So the change in length is going to be subtracting this minus this. So now we can define the normal strain, and I'll write it down here in the x direction, like so. So the normal strain that's going in the x direction is going to be, and now leave a little bit of space because we're going to take a limit, of the change in length. That's going to be u at x plus delta x minus the movement at the left-hand end. So that's going to be minus u at x, all divided by delta x. And then we're going to take the limit as delta x goes to 0. So there is our limiting process. That's what gets this to a measure of being pointwise. Well, it doesn't take too long for us to recognize that we've seen this before. That's from calculus. That's just the derivative of u with respect to x. So epsilon x is going to be equal to du by dx, the change in the axial displacement as we move along the length. So that's actually a better representation for us. So we write it like so. Now, at this point, we're going to do something that may look like it's completely unnecessary, because if we look at the subscript x, what does that mean? That means that our infinitesimal line element was originally oriented in the x direction. So yx, because our delta x was in the x direction. But for reasons that are a little bit beyond what we need to discuss right now, we're actually going to put in two subscripts. So we are going to use, I'll say we will formally use 2, epsilon xx. So that's going to be, and it actually turns out to be the partial derivative of u with respect to x. So we would write it like this, partial u, partial x. Rather than the ordinary derivative, we have line elements that are in a 3D medium. So that's the more general statement then that we would have for the normal strain in the x direction. If, however, we do have a nice simple bar, then we don't have to use this particular expression. This is relatively complicated. This is a first order ODE. And it says that the strain is related to the derivative of the axial displacement. So we can think about that, but in terms of the analysis method that we'll need in this class, we will rarely use this. So we are rarely, I'll say rarely required. And the reason for that is we are going to actually have problems that do have average or uniform strain. But I want you to see that this is the one that is a little bit more complicated. That's very robust. And from that, we can use all of the other statements that we might have. So in our class, in Civ 360, yes, it's important for you to recognize this, that there is a normal strain symbol, epsilon. It has two subscripts and it's a partial derivative. But very frequently, we will be able to get away with saying that epsilon xx is just the delta divided by L. So we're going to assume that there is a state of uniform strain. We're not going to worry about the silly putty and aluminum examples. If we do, we'll have to kind of put things together. But this is frequently going to be enough. So for right now, you're measuring normal strain as change in length over length is a good thing to do. So we want to commit that one to memory. Memorize that for now. The cool thing about this is it does have a sign convention. And it might be what you expect. If the line element grows, if delta x gets bigger, it's stretching and it's going to be a positive normal strain. If our line element length gets smaller, it is going to be negative. That's our shorthand. Plus IVE, minus IV, positive or negative. And notice how that meshes with normal stress. So we'll put that parenthetically. Meshes with normal stress, the sign of the normal stress. And that's a great place to end the first part of today's lecture.